here we shall have to suffer more, because I will start writing various equations, and this is exactly where I will need the blackboard, and I will be using this more intensely, I think, today. So, what I want to do now, we know how galaxies look, we know how the gas within galaxies moves, we know what magnetic fields are observed. It's now time to try to put everything together and try to explain what is observed. So, first I will try to argue that the observations do require some sort of dynamo action to be explained. And when doing this, I will make a very strong and very perhaps controversial statement where I will invite your criticisms. Then, accepting that I will be successful here, it will be worth to look into dynamo equations, and in our case this will be disk dynamo equations. And I will argue that this is a big advantage, that having a thin disk with intrinsic small parameter is a huge advantage, which will allow us further down to develop very simple and very useful, not one, but several, very useful and very simple analytical solutions of these equations. Now, the word analytical with the development of computers. The word analytical more and more often is perceived as derogatory. Analytical means unrealistic. Analytical means strong assumptions are made. Analytical means useless. And this is a dangerous tendency. I completely disagree with this tendency, and I will try to demonstrate how useful are these solutions. Anyway, the better are numerical simulations, the harder they are to interpret. Very simple, old numerical simulations could be just interpreted by just looking at a few graphs and understanding what's happening. The more complicated that be hard. Now, the modern numerical simulations are at the level of experiment, of laboratory experiment. So, you need serious techniques to interpret them. And I hope numerical simulations will not develop any further. Because having the sun in your computer isn't much better than having the sun in the skies. It will be equally complicated. What you gain by having the sun in your computer? Only that you can repeat your run for several suns and water. The more complicated is physics within your computer, the harder it is to understand what is happening. And here, simple models, the use of simple models is absolutely indispensable. In this sense, just giving just one example, it has become now in the papers produced here in this group in no detail. It has become standard, first using this test field method, a quantitative way to understand what exactly you have in your numerical simulations, and then comparing your numerical results with the solution of a simple system. So this is a standard way of thinking, by deduction, by analysis. You have a complicated system, you reduce it to a set of simpler systems, each of which captures only part of reality. And this is exactly why analytical solutions and especially approximate solutions play an important role. So, the importance of analytical solutions must grow rather than decrease with the development of numerical and experimental methods. So, I will start with two citations to illustrate the state of the art, the attitude of astronomers to magnetic fields. It is different from the attitude of geophysicists or solar physicists to magnetic fields. But we are talking about galactic dynamo, so it's relevant. I will just read it. The argument in the past is Volcher. He's a very clever, very witty person. The date is if I remember correctly, 67. 1967, yes. So these words are now 40 years old. The argument in the past has frequently been a process of elimination. One observed certain phenomena, and one investigated what part of the phenomena could be explained. Then the unexplained part was taken to show the effects of the magnetic field. It is clear in this case that the larger one's ignorance, the stronger the magnetic field. Absolutely true. So magnetic fields have developed a very notorious reputation. They're hard to understand. They're hard to understand. Therefore, if you can avoid using them, just don't use them. Forget about them. And this is the attitude of even now, of a large majority of astronomers and classical astrophysicists. This is another quote of 1990, right? 1990, of Don Cox. As usual in astrophysics, the way out of a difficulty is to invoke the poorly understood magnetic field. One tends to ignore the field so long as one can get away with it. And this is what most people are doing, even now. But now the situation is changing, mainly because of the new observational data, new satellite missions, which are providing the data which are directly dependent on magnetic fields. From the outset, we know that magnetic fields are important. So, the situation is changing, and it's the right time to work on galactic magnetic fields now. Observational data becoming more reliable and rich. Theory moves forward. Numerical simulations are becoming really fantastically useful. So, let's continue with this introduction. Let's continue. So, you remember what I was showing you, the structure of magnetic fields in galaxies. Generally, these are spirals. If we look at the disk face on, if this is a galaxy, then magnetic lines, when seen projected on the horizontal plane, they look like spirals. And first, originally, now I automatically, since I'm drawing magnetic field, I put the arrows, right? But observations, early observations, were not giving us the direction of the arrows. These were not known. Only the orientation magnetic field was known from the polarization planes of synchronization. And then it's very tempting, and this object rotates differentially. And then it was very tempting to attribute this field to just twisting of a homogeneous primordial magnetic field by differential rotation. And this was a very powerful idea, very simple, very appealing, physically simple idea, which was prevalent until maybe the 90s. So, the question arises, can magnetic field observed be primordial? Do we need any dynamation? Do we need all this trouble of deciding what is alpha effect and what is not? What is the turbulent diffusion? Do we need all this trouble? Before we continue, I prefer to define what I will mean by dynamation. Dynamation, conversion of kinetic energy into magnetic energy, which also happens if I have an external magnetic field. Imagine that I have a differential rotating disk with homogeneous magnetic field embedded in it. If the disk rotates differentially, very quickly, this magnetic line will be twisted to this sort of a configuration. So, the field has become stronger. I have kinetic energy converted into magnetic energy. But it is done in the presence of external field. This field is maintained by currents somewhere at infinity. This is not dynamo action. Dynamo action requires that this is a self-sustained magnetic field. So that there are no electric currents, no electromotive force at infinity. And this is a very important addition to the definition. So dynamo action means self-sustained magnetic field, independently of external sources. So, and you can find this is a very widespread opinion among astronomers. If magnetic Reynolds number is very large, this meaning that electrical conductivity, yes, please.
Excuse me, the condensation of a magnetic field following rho to the 2/3 or something.
Yes.
Would that, I know the dynamics will require dynamos, but just for the value of the magnetic field, would that be enough
More or less, yes. I will make these estimates.
Okay.
I will try to make the point against the dynamo as strong as I reasonably can, without really lying. I will try to honestly represent the case. I will try my best with it. Yes. For the strength, it's okay. Yeah. So, very high electrical conductivity. This means that magnetic fields, if they haven't been created somehow, will decay only slowly. So, you don't need to maintain it. It simply doesn't decay. Why problem? Why do you need all these dynamos? Okay, in the sun you need it, because you see that the field changes every 22 years. So you need to do something non-trivial to change the direction. In the Earth also, first the decay time is relatively short, RM isn't that large. Second, you see all this reversal, stuff like that. But in galaxies, you don't have to worry. Why? The decay time is very long. I will make an estimate on the next slide. It's 10 to the 22nd years. It's 12 orders of magnitude, the decay time of the galactic magnetic field, due to ohmic diffusion. 12 orders of magnitude longer than the age of the universe. Do you need to worry? But what I want to say now, before I continue, that this statement is not true in turbulent systems. However large is the Reynolds number. If your system is turbulent systems, they are like predators. They eat all the energy which is injected into them. So if I plot, say, magnetic and kinetic energies, the spectra, power spectra of turbulence, so there is some energy range scale, and this is a typical spectrum, right? What happens here, the turbulence leaves by constantly transferring energy from large scale where it is injected to small scale where it is lost to heat. Right? By definition, this was turbulence. The transfer time is of the order of L0 over U0, the correlation time of turbulence, addition over time. So, whatever energy you will inject at this scale, over this kinematic time, this energy will be lost to heat. Does this time depend on viscosity? No. Does this time depend on magnetic diffusivity? No. Even if RM is very large, still the decay time, the time to convert magnetic or kinetic energy into heat will be the same, independently of the Reynolds number. This is what is called, this was the achievement of Kolmogorov's theory, the self-similar nature of turbulence. So, imagine that I injected magnetic field, I created magnetic field in the system. If the system is turbulent, in this time, this energy will be converted into heat, whatever the Reynolds number. So, even if the Reynolds number is high, but the system is turbulent, magnetic field can be magnetized. It needs to be explained. You cannot just wave your hand and say, ohmic losses are so low that I will not bother about explaining magnetic fields. You need to explain them. So then the conclusion, which is controversial, and I would appreciate your objections, is that any three-dimensional MHD, I don't know, I'm not sure about plasma effects, I'm sure that dynamo can't work in two dimensions. This is why I make these qualifications. So any three-dimensional MHD system, if only it's turbulent, and if only I know that it possesses magnetic fields, must be a dynamo. If only there are magnetic fields in a turbulent system, there must be a dynamo. There is no other way to explain them, irrespectively of the values of Reynolds numbers. The higher the Reynolds, well, only for low Reynolds number, ironically, I can get away without dynamo action, because for low Reynolds number there will be no turbulence, and the magnetic field can indeed live during the ohmic, perhaps still long ohmic diffusion time. Moreover, imagine that there is no turbulence, but I have a random magnetic field. then this magnetic field will drive, via the Lorentz force, will drive its own motions, right? If Reynolds number is high, these motions will become turbulent, and the magnetic field will kill itself. So, for magnetic field strong enough and non-homogeneous, even this requirement for a system to be turbulent isn't needed. It will become turbulent automatically if Reynolds number is high enough. So the statement looks to me very strong. This means that if you look, wherever you look, at any object in the sky, check if it is turbulent, check if it is magnetized. If the answers are yes to both questions, check if there is any magnetic field at infinity. If the answer is negative, write a paper about dynamic action of that object. Put a bet on just in case. If you lose, at least you will have money back. I would appreciate objections. So, let's now discuss why we think that in galaxies specifically, well, these arguments, because they are so generic, of course will not be accepted by many people. You cannot say just because of this, I'm sure that galaxies have dynamics. People want specific arguments. I'm coming now to specific arguments. The idea that magnetic field of the galaxy is just a primordial field twisted by differential rotation was historically the first explanation of galactic magnetic fields. Suggested in the 50s. It's a natural idea. And then it was Jim Parker in Chicago who proposed this argument immediately after the suggestion. So, first, the decay problem. Primordial magnetic field. How long will it take for primordial magnetic field embedded into the galactic disk to decay? Let's make this estimate. Ohmic decay. This is what is known as a Spitzer magnetic diffusivity. So this is the magnetic diffusivity in a fully ionized hydrogen plasma. This can depend only on temperature. I know the velocities. I know the half thickness of a galactic disk. I can calculate the Reynolds number based on this, and it's equal to 10 to the 20th, enormous numbers. Then the decay time will be equal to this h squared, the scale of the field, squared, divided by eta, 10 to the 27th years. So I made a mistake. It's not 12 orders of magnitude longer than the Hubble's time. It's 16 orders of magnitude longer than Hubble's time. The problem is solved, right? It doesn't decay, and therefore nothing to explain. No, this was Parker's argument. This system, the galaxy, is turbulent. And the relevant time scale here should be not ohmic decay time, but turbulent decay time, because we are talking about the large scale, because we are confident that the field which we observe has the galactic scale rather than the turbulence. For the turbulent diffusivity, we can take the standard mixing length estimate for the turbulent diffusivity. It's equal, essentially, to the product of turbulent scale and turbulent velocity. We have it here. It's sort of, 19 orders of magnitude larger than the ohmic diffusivity. And the decay time correspondingly is just 20 times shorter than the galactic. 20 times shorter than the galactic light. So, without dynamo action, the large-scale magnetic field will be destroyed. Well, what are possible objections to this idea? That, well, this turbulent diffusivity, who measured it? How you know that there will be turbulent diffusivity? There will be always something happening which will prevent this from working. It's hand-waving. Of course, you can always find the case where turbulent diffusivity is suppressed. But just the experiment of me dropping a little bit of good French perfume here for you to enjoy the smell over there will still make my point stronger. The turbulent diffusivity is an experimental and theoretical well established. Still, this argument, because of that, well, we start now from turbulent diffusivity. Because of that, this argument wasn't completely convincing to many people. Especially if you don't want to be convinced, right? If you don't want to be convinced, it's very hard to do that. There was another argument, again suggested by Park. Again, let's consider a primordial magnetic field embedded in differential rotating disk. Now it rotates in the negative direction here, just because these diagrams are borrowed from the book of Keith Moffat. It is a simulation of Parker, of different Parker. So what will happen with this field? It will be twisted like here, but with each rotation in the disk, there will be one turn of the magnetic power, right, of magnetic line. So after 1, 2, 3, 4, 5, 6 rotations, I will get a picture like that. And the field will be alternating along the radius very quickly. What will happen is that now, if you recall that there is even weak diffusion, there will start reconnections between these magnetic lines. Therefore, very quickly, magnetic field will be eliminated, reconnected here, and very little will remain. So this is the result of very early numerical simulations. After a while, magnetic field within the region of closed streamlines becomes weak. In Moffat's book, and it was, for example, Nigel Weiss who has contributed quite a lot to understanding this situation. So, expulsion of magnetic field from a region with closed streamlines. This one is called. If you have a region with closed streamlines, magnetic field will be expelled from this region. And the strength of magnetic field will vary in time in the following way. First, during the time when magnetic field is stretched by differential rotation, its strength will grow. And this growth will be linear in time. Linear, not exponential, linear in time. Because after each rotation, the field is doubled. It's linear. It's a linear growth. But then, as soon as the separation of these magnetic lines will become small enough for magnetic diffusivity to kick in, the field will exponentially decrease to come to this state. And this is the most important part of this slide has been truncated. It's the continuation is Andrew Beckley. It's his simulation. Now let's see how it happens. I have here, I will show you a rotating fluid. It's a two-dimensional problem with omega directed towards you, away from you, away from you. Yes, so it is a positive rotation, right? The profile of omega is e to the power minus r squared, minus the distance from the center squared. So Gaussian profile of omega. I will start with magnetic field, which is directed purely vertically, like this. There are no arrows, but that direction doesn't matter. Actually, can I just add an arrow right here on the screen? No? Okay, fine. Then we shall continue without arrows.
But just move the upwards, that's fine. Then you can do it.
No, it's okay, it's okay. So now there will be a movie showing what will be happening with this magnetic line. Probably I should better click here rather than this clicker. I will repeat it again.
How's it calculated?
This is one. Andrew will be explaining this model in his seminar talk. So here, magnetic field is frozen into the flow until magnetic lines come into close contact close enough. In fact, it's you can see this distance where they start reconnecting, and then if they're close enough and oriented properly, they just reconnect. So this is just reconnection. So what you see here, that first, that it starts rotating, first magnetic field becomes stronger, stronger and stronger within the whole volume. But then, as soon as this distance becomes shorter than the reconnection length, they start reconnecting, and you see that this area, the vortex, becomes free, gradually free of magnetic field. So let's see it again. So it gets stronger and stronger, and now reconnections start, and there is no way to resist the reconnections. This is the reconnection length, right? And eventually, you evacuate magnetic field from the center. It's completely reconnected. After a few rotations, after just a few rotations, yes,
I think it would be good to recapitulate that the objections against this are always connected with the fact that the magnetic field has finite strength. And indeed, even Parker in his latest review has this objection. Even though he was counteracting these objections in the late 70s, he actually...
Why the strength is important?
Why the Lorentz force back reacts, of course. The question is exactly when.
On differential rotation? No.
No, on the turbulence, yeah.
And suppresses turbulent diffusivity,
yes,
for example,
really
right?
Strong field. I mean, obviously turbulence will end up going all around.
Yeah. And suppresses turbulent diffusivity. Correct? Yeah. Yes. But it can happen. It can happen, yes. It can happen. Because the turbulent diffusivity is eta or beta. I prefer beta, the notation introduced in Potsdam in the 60s, is 1/3 U squared average tau. Of course, U squared will be affected, and can be affected in a very subtle way. For example, you can use various anisotropies. Yes, perhaps. But, why should I feel guilty? Show me that under galactic conditions, this does indeed happen. Because in galaxies are special objects. Here the turbulence is driven by explicit brute force of supernova explosions. Can magnetic field prevent a supernova bubble from expanding? Come on, it's a joke. So when you will tell me that turbulent diffusivity driven by supernova explosions will be affected by magnetic field in galaxies, it will be difficult for me to continue discussion. In the Sun, perhaps. In the Earth, perhaps, where turbulence evolves due to instabilities. But in the galaxies, it's driven by explosions of supernova stars. So, magnetic field cannot prevent those stars from exploding. And moreover, to the first approximation, these explosions will maintain this isotropic turbulence.
Oh, and we know two things. On the one hand, we know that in 2 dimensions, it's really true, of course.
What?
The turbulent diffusion is really suppressed in an RM-dependent fashion. That's
turbulent diffusion driven by supernovae, right? By brute external force.
probably actually that too, yes, if it was in 2 dimensions.
Mm-hmm.
So that would be really proportional to 1 over RM.
Okay.
That's understood, because it has to do with the conservation of the magnetic vector potential squared.
In 2 dimensions, yes.
In 2 dimensions, yeah.
Mm-hmm.
So therefore, that would be a good benchmark for that theory. So that is not usually reproduced in all simulations. However, in 3 dimensions, that has never been seen, and it also is not expected, of course. And indeed, what has been seen is that by increasing the Reynolds number from 2 to 600, for example, eta t goes down by a factor of only 5. What happens after that is unclear from the simulations. So simulation-wise, there is no evidence for anything catastrophic, and maybe that's, as far as I'm concerned, the strongest argument. And in 2D, it's indeed true, but this really is 2D, and there's a major difference between 2D and 3D.
But still, it's useful to look at it. Still, it directs your attention to right things. Yeah, but still, I think that in this situation, accepting that these nonlinear effects will destroy turbulent diffusivity, and assume that they will not destroy, these 2 viewpoints have equal basis. There are equal number of arguments both ways.
There's a question
I was just wondering if reconnection can drive turbulence.
Yes, at smaller scales, right? At the scales of basically of roughly reconnection scale.
Well, this
it can.
reconnection does couple to larger scales. I mean, it's very localized phenomenon on experiences, but lately there are many theories about turbulence driven by reconnection.
Yeah, but with galaxies, I'm in a very favorable position. I don't need to worry. I just see these sources of turbulence. They're just here in front of me. All these atomic explosions occurring every 50 years in the galaxy, just in front of me. Yeah.
what you're showing here is for a vortex which is stationary, right?
Absolutely stationary, yes.
Okay. Now, I understand the galaxies that may be the case, but the decay, the increase in decay you have as a time scale.
Yes.
It would be interesting to compare the time scale to the eventual longevity
Yes.
of the vortex.
Agree.
Because you might not reach a steady state.
Yes. Here we are.
Okay.
Will do. Will do. So let's look at this this configuration. What is here beyond the margin is delta r. I will denote this distance, delta r, is a function of t. The radius of the rotating vortex is big R. Where is big R? R naught. Big R naught. And I will need the following variables. R d omega by dr is denoted with G. This G is here. And the turbulent Reynolds number, C omega, it's called C omega, this C omega, is equal to G R naught squared over beta. This is the convenient definition of the Reynolds number, which characterizes the amount of shear. So first, the growth will proceed during the time. This is the time, right? Oh no, this is delta R. Delta R, this distance, will be proportional to R naught and inversely proportional to the shear rate in time. The larger is t, the smaller will be this distance. This distance will decrease as 1 over t. And the rate of decrease is controlled by the amount of shear. Then immediately we can easily calculate what is known as the pitch angle of magnetic lines. The arctan of the radial component of the field to the azimuthal component. It will decrease as 1 over gt. So with every turn, the magnetic lines become tighter and tighter wound. Then, when the growth will be stopped by diffusion, when the amplification time will be of the order of the diffusion time. The diffusion time is here. This is delta R divided by beta. The amplification time is of the order, is this given by this G. From this I immediately get the time, since I know the expression for delta R. Then T will be the larger C omega Reynolds number, the longer will be the growth. The stronger is the shear, the shorter will be the growth. So I can estimate the time corresponding to this point. This is my T naught. And then the pitch angle at this time, so when I replace this T by this T naught, the pitch angle at the time of maximum field strength will be equal to minus C omega Reynolds number to the power minus 1/2. Fine. What will be the maximum field strength? It's linear growth during for the time T naught, it's B naught, initial field, times G times T naught, which is B naught to the power C omega to the power 1/2. And the separation of magnetic lines at the moment when the field is the strongest is C omega, the root of C omega times smaller than R naught. So, sort of, all these estimates can easily be done. Let's see how it looks in the galaxy. And the galaxy G is of the order of the radiation velocity divided by the radius. Beta I know. These are all observable quantities. I estimate C omega immediately. It's of the order of 600 or 6,000. 6,000. There is one more zero here.
We should change this maybe. Should we fix that? Should we fix that? This is
Can we?
screen.
I think it's the problem with the projector, right?
You can change the resolution.
Oh, no. Changing resolution will destroy my it will take our changing resolution. Are you sure it's resolution?
Maybe it's better this way.
Let's continue.
Yeah, this is better.
Oh no, there will be, because it can be a problem with because all three laptops we have today all have the same problem, right?
Perhaps.
So maybe it's better to change one projector than all laptops. What do you think is better?
It's amazing, right? But I mean, can we of course go to this? Is that what it is?
Let's try. 2 is the outer screen, and 1 was the internal screen.
Okay. And then we go to
And let's try F5. Does it? Is it better? Well done, Axel. Never expected that. So I suggest that everybody changes their settings in their laptop. So this is our G, this beta, this I can calculate. All these quantities are observed. There's very little freedom to change it. Fine. Now I can calculate the pitch angle at the time where the field is maximum, -1 degree. It's very difficult to change this. The distance between this distance, delta r, is 100 parsecs. It's of the order of turbulence scale. Maximum magnetic field, if initial magnetic field is 10 to the -9th, like the upper limit on the intergalactic field, I will get 10 times weaker than the observed fields. But as Jean-Francois said, if this field is first compressed by collapsing cloud, it can become of the order of, 10 to the -5 to the power 2/3, 100 times stronger. And then it will be fine. The maximum strength is okay, but it's a maximum strength. Here, I'm fantastically generous. In discussing this mechanism, I'm fantastically generous. I'm just taking the maximum field strength. And we can't expect all the galaxies to sit on the maximum. So, you should appreciate my generosity, right? It's extraordinary generosity. So, the picture we get, that the best we can have is magnetic field, say, let's put 1 microgauss, but its pitch angle will be -1. What we observe, pitch angle by a factor of 10 larger, the scale of the field is definitely 10 times larger, and magnetic field, okay, fine, let's accept it. So, what is the objection? Well, what would I say? Forget about diffusivity, it's a turbulent system. You should in fact use here, yes, okay, fine. Yeah. You should in fact use something else. Say, use stronger turbulent diffusion, because turbulent diffusion will slip, it will not be twisted that strong. And the pitch angle will be okay, right? Because it will slip through the plasma. But if you now include turbulent diffusion, you hit this one. If you want turbulent diffusion to avoid tightly wound spirals, then it will decay. If you don't want decay, you will say that turbulent diffusion is suppressed. And then you will hit this problem. So what do you prefer? Which of the two problems you prefer? Each of them kills you. You cannot solve them simultaneously. So you save your head, you lose your tail. You save your tail, you lose your head. You need to fly. You need to fly. You have to invoke dynamo action. And this will help. Just don't sit in this swamp. Just fly. Is it convincing or not? Any objections? This is a picture which cannot be explained by this. You either explain the strength or you explain the geometry of this field. You cannot explain both with frozen in magnetic field. Now, if you look here, this alternating magnetic fields, right? This is the mode m equal to 1. Obviously, right? You have the initial field, which has the symmetry m equal to 1. Then you apply differential rotation to it, and this structure will have m equal to 1. Along each circle, the field changes its direction. What is observed is a roughly axisymmetric magnetic field. And here is the one feature of all this thing. Until mid-90s, or early 90s, the analysis of such pictures, the observations had rather low accuracy, low resolution and sensitivity. And people were coming, in part, under the influence of theory. Observers were concluding that indeed m equal to 1 mode dominates in the majority of galaxies. And quite a number of groups spent quite a long time trying to explain how the dynamo can have m equal to 1 mode dominant in such disks without success. So it looked like a huge problem for dynamo theory. It can't explain the dominant bisymmetric symmetry m equal to 1 mode in galaxies. But then what happened was that in the 90s, late 80s and 90s, first the quality of observation was improved. and perhaps more significantly, the quality of data interpretation was improved. Instead of just looking at the plots and not calculating errors correctly, there were introduced methods of data analysis made based on rigorous statistical criteria and reasonable estimates of the errors. So together, better observations and better analysis changed the picture completely. In the mid-90s, it became clear that most galaxies host axisymmetric fields, distorted by various things. What seemed to be a horrible difficulty for dynamo theory all of a sudden became a prediction of dynamo theory, which was gloriously confirmed by observations. But it was hard time. You had to be quite stubborn to maintain your viewpoint when there was such a strong, overwhelming evidence against the dynamo theory. It was hard time. But then the reward was enormous. So, and I will give, and I also showed you more examples. For example, whatever you tell me about turbulent diffusivity or whatever else, just this galaxy, which has this sort of a structure, axisymmetric structure within the disk, which is already impossible to explain by a frozen magnetic field. It's in the disk. Moreover, in the halo, it has an entirely different configuration. Not this, like this. An entirely different configuration. No primordial theory can explain such situations. And in my previous lectures, I was trying to present explicit arguments in favor of magnetic field not being frozen into the flow. Primordial theory requires that the field is frozen to a very large extent at least to the flow. So this is interesting. So, is it worth continuing with dynamo equations or not? Is it interesting? I hope it is. I hope it is. I think that arguments in favor of primordial theory only work if you neglect most of the observational facts about galaxies and concentrate on only one of them. So, let's look into equations now. I will denote the large-scale magnetic field with just big letter B. Letter small b will stand for the small-scale magnetic field. So no zeros, no over bars. I will try to make my notation as simple as possible. And I want to analyze this equation. Alpha dynamo, this is the alpha effect. This is the rotation, mainly the differential rotation. This is the turbulent diffusivity. Appropriately to galaxies, I will introduce cylindrical coordinates, r, phi, z. I will align my z-axis with the angular velocity. And then, in this coordinate system, my large-scale velocity will consist of differential rotation, where omega, to the lowest approximation, can be considered to be a function of cylindrical radius alone. I will consider a thin disk whose thickness is of the order of h, h, radius is r, and big R is much larger than h. What are the simplifications which I can use? First, in a thin disk, the vertical derivatives, d by dz, will be much larger than the radial or azimuthal derivatives. So this number squared b, to the first approximation, only contains the second derivative from z. And I will also, to start with, we'll consider axial symmetry. This can look questionable, but in fact this assumption is not as bad as it looks at first sight. This galaxy, I will assume that this galaxy is actually symmetric. Looks a horrible assumption, right? Look at these arcs. They are obviously it's a deviation from axial symmetry. But this is a visual picture, and perhaps I mentioned it in my first lecture, that in fact, in terms of the gravitational potential and velocities, this spiral pattern is just a weak perturbation. The typical rotational velocity is of the order of 200 kilometers per second. The typical velocities associated with deviations from axial symmetry is of the order of 10 or 30 kilometers per second. So the ratio of the non-axisymmetric velocities, u, divided by the rotational velocities, is of the order of, say, 30 to be generous, to 200. 3 divided by 20 is so 10% maximum, right? The order of 10%. So, in fact, this disk is quite a meaningful approximation to consider this disk to the lowest approximation to be absolutely symmetric. And then, of course, we can, let's first try something simple, and then, if we shall be successful, we can improve our picture. So, first, a few words. Kando, I didn't have these slides here, but Kando told me that I must. Okay, fine. So, a few cartoons explaining the nature of the alpha effect. First, if I include this term alpha here, I need to understand what is the origin of this term, of the helicity of turbulence in the galactic disk. This is a natural consequence of rotation and density stratification. If I have a random flow here in this disk whose density decreases with height, then let's consider a volume element, turbulent element, just raising up just because of either buoyancy or because of random causes. As it raises up, and if this distance is comparable to the pressure scale height, it will expand. As soon as it will start expanding, the Coriolis force will twist it. And all raising elements in this northern hemisphere will be twisted in the same way. Now, if I will consider a fluid element which goes down instead, it will contract. It will be twisted in the opposite direction, but the dot product of the vertical velocity and additional omega will be the same, with the same sign. So all the fluid elements which move due to random causes vertically will have the same sign of helicity. Likewise in the southern hemisphere. And the very useful formula, Karl-Heinz, it was 1967, right, that Fritz derived this formula. I think he never published it. Is it true? It was in his thesis.
Well, it's in a more developed form, not this.
Yes, yes. But, you know, very often more developed forms are harder to use. So, this is a formula I like. It tells you that alpha is proportional to turbulence scale. If there is no turbulence, there is nothing to talk about. The stronger is the rotation, the larger will be alpha. And h is the pressure scale height. The larger is the pressure scale height. Homogeneous system means h tends to infinity. Alpha will tend to 0. So this formula contains all the physical elements of the process. I will be using this order of magnitude estimate in what follows. And then, first differential rotation. Of course, I cannot avoid discussing this twisting of magnetic field by differential rotation. It's unavoidable. It is there. So first, I will consider a magnetic line, and look at this. It's a magnetic line of quadrupolar parallels. I will show later that quadrupolar fields are dominant in the field. So I will start with a quadrupolar initial field, arbitrarily weak. So the magnetic line enters the disk from the side, travels within the disk along the, it's all in the plane of meridional field, and then goes up. Differential rotation will twist it into this configuration. Then, what the helical turbulence will do with such field? Let's consider just a small part of this magnetic line here. First, vertical motions, say let's consider vertical up, will create such loops here. Coriolis force will twist all the loops, all in one direction, and then, if these loops merge, they will create a magnetic field at a larger scale, because the direction of all these loops are all coherent. If you look carefully at the arrows, this arrow is directed in this direction. This one is directed inwards at the bottom. Then, and it's an important point, if this upper part is lost from the disk, that shown dashed, by turbulent diffusion, then the lower part will have exactly the same direction as here. These arrows are similarly directed. This means that now differential rotation acting on this lower part of the loop will again repeat this cycle, and the field can be self-sustained. Important features here. are that you do need to lose some field from the disk through the surface. Without that, this mechanism won't work. You can show this with just by manipulating the equations. I'm not doing it just to, but it's not just hand waving. I can look at the equation and I can prove that if the turbulent diffusivity is 0 here, closed boundary conditions, this machine will not work. It's important to remember in connection with flux of magnetic helicity and stuff like that. From the very beginning, if the disk is closed, the machine won't work. From the very beginning, we need open boundary conditions for the whole machine to work. Then it's not surprising that not only magnetic field, but many other things are lost through this. Yes.
By geometrical consideration, should we expect that the bottom part should go away too?
No, there is a symmetry. This is a symmetry plane.
Okay.
There is a solid floor here. It cannot. Symmetry. Everything in the lower part of the disk, symmetric events happen. So there will be another loop, again directed the same way like this and going asymmetrically. So here I have a maximum of the field. Above and below the midplane, there are similarly directed magnetic fields. Because I start here, there will be another loop below the midplane, which will go like this. And they will be the same direction. It will produce the same direction, even mode. There will be an even mode here, which will produce an even mode here as well.
But that's really because you know that the field is quadrupolar. If it's
Yes.
dipolar,
Well, I can also make a similar thing for dipolar field. Yes, it will also
then
work.
there would be interaction between north and south.
Yes. I can make a similar diagram for dipolar, but now I know what will happen later, right? I will show that this mode is generated faster in the disk. And such diagrams for dipolar modes are often shown in application to the sun of the Earth. Therefore, this is why I want to make a specific diagram for galaxies where quadrupolar mode dominates. Okay. But generally, this mechanism, under appropriate symmetry, can generate both quadrupolar and dipolar modes. Both of them can be generated. Continue.
And what?
Yes.
So going in the vertical direction, you need a gradient of turbulence intensity.
Yes. No. Wait a minute. Homogeneous turbulence will do that. I need the gradient of magnetic field. I need turbulent diffusion.
Yeah, but you need to change the turbulent diffusion.
No. Why? If I have, I need beta d2bz, or b, horizontal field, by bz squared. Beta can be constant, magnetic field should vary. Just normal standard diffusion. I don't need nothing exotic here. Just normal standard diffusion. B to second derivative on class n of b should be non-zero. By the way, with this stuff, there was a, maybe just a good time to tell you an anecdote. With these cosmological magnetic fields, can there exist magnetic fields from pre-galactic states? And there was an observation of Zeldovich in 1965 that imagined that the universe was created or born with homogeneous magnetic field, absolutely homogeneous. Homogeneous magnetic field cannot be destroyed. It's not subject to diffusion. Even with finite conductivity, if magnetic field is homogeneous, dB by dt is equal to curl of U cross B plus beta homogeneous arm doesn't matter. Number squared B. If magnetic field is homogeneous, this is gone. Perfectly homogeneous magnetic field in infinite space doesn't decay because it doesn't need currents to maintain. And therefore, the statement holds if the universe had a large scale homogeneous magnetic field in the very beginning, it will always be with us. It can't be eliminated. Yeah, it was somehow, for some period, it was quite an influential idea, I think. Okay, let's see what's next. So, now we discussed waving the hands, how it works. And now I want to see how this looks in terms of equations. So again, I will consider this equation. I will consider the disk to be axially symmetric. So no coefficients, this alpha, v, or beta, that don't depend on phi. Therefore, the solutions depend on phi as e to the power I and phi. And at some point, I will take into account that this ratio of disk thickness to the disk diameter is much less than 1. At some point, I will take advantage of the approximation. First, you take these equations. Imagine that you start your PhD, right? And your supervisor throws at you this equation and tells you to write it out in cylindrical components. You get this. Gosh. Then you start regretting the time when you decided to make a PhD, right? This is d by dt. This comes from here. All terms with Im come from differentiating b with respect to phi. D by d phi will give me Im. This term. M squared comes from the second derivative in azimuth. So these are terms with m. On the right, d by dz, d by dz, d by dr. This again, d by d phi's kick in. So the first, you feel desperate. It's impossible to start your PhD with these equations. But then, what helps is the idea, let's consider axisymmetric fields. It's impossible. Let's do something simple. Let's put m equal to 0. It's an improvement, right? It's an improvement. Many horrible terms are gone. What is left? d by dt, dr, fine. d by dz, d by dz, d by dr, and this epsilon. This epsilon is small, right? Okay, not bad. These are gone. Here, a similar operator on the left. This term, similar term to this. Again, vertical diffusion. This is horizontal diffusion. And here, some dirt coming from Bz. Look at Bz. d by Bz, vertical diffusion, radial diffusion, and some conversion of the azimuthal field into radial field. Fine, good enough. Moreover, we see now that all of a sudden, these terms in a thin disk are of different orders of magnitude. This epsilon square, if only not for this term, the equation will become much simpler. If I put epsilon here equal to 0, again it will be simple. Put epsilon here to 0, you get further simplification. So, but still, even with these epsilons, these equations already look solvable. And this, at least for me, this observation that there is a small parameter here if you introduce appropriate units. This basically made my PhD some long time ago. But still, epsilon is much less than 1. So be bold. Those who don't take risk never drink champagne. Put it equal to 0. We end up with a local problem in a disk. So in other words, if I have a disk, a thin disk, then magnetic field at this point will be affected by several effects. First, it will be affected by what happens here at fixed z. These will be these terms. And also, there will be diffusion of magnetic field from other radii. But this diffusion will be weak, at least much weaker than vertical diffusion, as long as the disk is thin. So, the first approximation, I assume that there is the action, what happens on neighboring points isn't important. It's equivalent to assuming that my disk has infinite extent, just infinite extent. It's a more of a slab, infinite slab. So I assume now that R0 tends to infinity. And this gives me these simple equations, local equations. I will be putting them very boundary conditions, but this is intuitive. Because this and this were equations which were in fact solved in 1972 by Gene Parker independently and Weinstein and Rosmaitin. It was the first paper about galactic dynamos published in 1971, where they made these bold assumptions. and then solve this system of equations. I've just collected only these terms here. This is the system. Second order in Z. Oh, look at this. What a nice feature. The equation for Bz, this approximation has split out from these two equations. The first two equations don't contain Bz, and the third equation doesn't contain Br and B5 to this order. Fantastic. Instead of 3 equations, we have just 2 to solve. This is where you start working on your PhD. This is where you start sort of recover and start writing various equations. Of course, it doesn't mean to this approximation Bz will decay to 0. So in a thin disk, to the lowest approximation, magnitude is horizontal, but only to the lowest approximation. It cannot be purely horizontal everywhere, because the divergence of B should be equal to 0. But it can be shown that exactly if you obtain Br and B5 from these equations, and then calculate Bz from some invariant condition, you will get the same result as obtaining Bz from the full system of equations. So in this case, what I can do, and I can calculate Br and B5 from the first two equations and restore Bz from some invariant condition. The resulting Bz will be much weaker than Br and B5. Well, as weak as small is the epsilon. For small epsilon, Bz will be weak. So all the ends meet. It seems to be a more or less closed model. So I will introduce obviously dimensionless variables. Dimensionless z with tilde is z divided by h. Dimensionless time is normalized to the diffusion time. Immediately after that, I will get dimensionless numbers here. R alpha characterizes the strength of the alpha effect. R omega characterizes the strength of shear. G is R d omega by dr, the amount of shear. So this is now I will drop tildes just to make my notation simple. So these are the dimensionless equations we have. So this term describes how Br is generated from B5 via the alpha effect. This term describes how B5 is produced from Br by differential rotation. And also the same can be done by the alpha effect. If I combine these two terms, the dynamo will be called alpha squared dynamo. If I combine these two terms and neglect this one, the dynamo will be called alpha omega dynamo. If I keep everything, people often call it alpha squared. So this is what I will do. I really want to start with something very simple. So I will indeed neglect this term here, comparison with this one, because R omega, we shall estimate this value. R omega is of the order of 10, and R alpha is of the order of 1. So this term is indeed is expected to be significantly larger than this one. I neglect the second term. I will have this system of equations. It can be simplified even further. Look what I can do. I can absorb this R alpha into B5 or BR at matter of taste. I can redefine my magnetic field components. For example, let's divide this by R alpha. I will get 1 over R alpha BR is equal to term without R alpha, BR divided by R alpha. I will introduce new BR, BR dash, BR over R alpha. Then R alpha will disappear from here, and here it will be multiplied, R omega will be multiplied by R alpha. I will get what is called the dynamo number, the product of the two. So this system is controlled by one single control parameter, known as the dynamo number. Just one single control parameter. It's probably time to look at the boundary conditions. If the disk is surrounded by a non-conducting medium, which often is described using the word vacuum, so no electric currents outside the disk, then I will not be spending time to justify these boundary conditions. Then azimuthal field must be exactly equal to 0 on the surface. And as long as the disk is thin, the radial magnetic field will also be equal to 0 on the surface. This means that in an infinite slab, let's start, better let's consider a more realistic picture. If I have a finite disk like this, then magnetic lines will behave a quarter-polar mode, like this, right? They will have some vertical, some radial component of magnetic field on the surface. But the thinner becomes the disk, the smaller will be this radial component, just from symmetry, right? If the slab is infinite, this direction and this direction are equivalent. And magnetic lines will leave the disk purely vertically. They can behave, do whatever they want later, but they will all leave the infinitely thin slab exactly normally to the surface. Exactly normally to the surface. So, on the surface, BR will be equal to 0. So, it is an approximate relation. BR for Z equal to 0, to 1, the surface, sorry, is of the order of epsilon. So, this is H over R. As long as we decided to put epsilon equal to 0, we have to put this equal to 0. In the next order, when we shall include the radial derivatives, these boundary conditions should be taken, BR will be known. For Z equal to 0, I will adopt just symmetry boundary conditions. I will now take advantage of the symmetry with respect to the mid-plane, Z equal to 0. I will consider two families of modes, quadrupolar modes of this type, where the azimuthal field B phi has a maximum at Z equal to 0. So dB phi by dz at the midplane is equal to 0. Likewise, BR will also, BR is this radial field, is also maximum at the midplane. So this will be my boundary conditions, which will, or symmetry conditions, which will isolate quadrupolar modes. For dipolar modes, azimuthal field is an odd function of Z. So at the symmetry plane, B phi, it must be B phi, sorry. This must be B phi. B phi and BR are both equal to 0. You see the midplane, the magnetic line goes exactly vertically. From symmetry, BZ must be equal, BR must be equal to 0 here. So this completes my problem. Now I have an idea. Yes, yes, please.
Do you see any signature from one of those two modes from observations?
In the Milky Way, yes.
Yeah,
you remember I was showing you this very transforms of RMs.
Yeah.
Big red spot and big blue spot,
yes, yes.
which are symmetrical with respect to
Okay.
like here.
Okay.
But again, only we have this evidence only in the Milky Way from observations. For external galaxies, because I don't have time to discuss it here, but I know why. But I can explain why. But I will just make a statement. For external galaxies, it's difficult to decide what is the symmetry of the field there. So this is based only on observation in one single galaxy, the Milky Way.
But I think it's natural to assume if it happens in the Milky Way, it might happen in other galaxies.
Hopefully. But my Milky Way has reversals, which other galaxies probably don't have. So it's difficult. But still, this difference, the dominance of quadrupoles in thin disks is so strong, I think that everybody accepts that in most cases, at least in most regions, in the bulk of the volume, quadrupolar fields should dominate. I think this is more or less well accepted. It doesn't mean that it's correct. Jean-François.
Using the boundary conditions on your previous equation, can you turn the system into d dipole dt equal and d quadrupole dt equal
Yes.
with interactions?
I can if needed. But interactions will be non-linear, right? Linear system just splits.
Yeah, I know.
Yes. Interactions will be non-linear. And then, well, I can, yes, of course I can. But as we shall see, that in a thin disk, under realistic conditions, the dipole, the difference in the generation thresholds, in the marginal dynamo numbers, is huge. The quadrupoles can be generated when this dynamo number, this one, exceeds by modulus 10. Dipolar modes need, I think, 300 to be generated.
Right, but if you have some dynamics at some points, if that quadrupolar modes as with voltage 5, we will need to have another mode to change density.
Perhaps, but there are also radial modes. There will, thin disk, there will be many radial modes.
Oh, okay.
One vertical and many radial.
Okay.
So, in terms of quantum mechanics, these energy levels, the dipole and quadrupolar, will be widely separated.
Okay.
But each will be split into a dense multipoles of radial modes. So first there will be interaction within each multipole.
And
And with them, they will interact with each other.
And the radial modes are the ones that interact during the dynamics then?
I think so, yes. They can create these reversals along the radius.
Okay.
But still, the importance of dipolar modes in galactic dynamos is still not well understood. For example, dynamo numbers, you need dynamo numbers for the 300 to generate them. Such dynamo numbers can occur in the central parts of galaxies. And moreover, there are many people who do believe that in the central parts of galaxies, indeed, the field has a dipole structure. But these central parts of galaxies are physically complicated regions. It's very difficult to decide what exactly happens here. But we should keep our eyes open to dipolar modes. They can turn out to be more important than we think. There was one more question, no? Okay, now let's make these estimates. Now we have our equations. There's just one single parameter d here. So what's the value of d in galaxies? I will make estimates, as everybody else does, for the solar neighborhood in the Milky Way. But from the very beginning, I want to make it clear, absolutely clear, that it's one isolated place in the universe. These estimates will be useful to me, but it doesn't mean that this estimate will apply to other places in other galaxies. So with this reservation, let's start. Rotation. Omega, as we discussed in the first lecture, the rotation curves, v as a rotational velocity as function of r, is almost flat. So omega is proportional to 1 over r. This we know from observations. The rotation velocity is 200. The radius, let's take 10 kiloparsecs, roughly distance from the sun to the galactic center. The escape height of ionized gas, which can cause magnetic field, is of the order of half a kiloparsec. So this our epsilon, this ratio of the disk half thickness to radius, or full thickness to diameter, is 0.5 divided by 10, 5%. So this is how thin is our disk, 5% for the aspect ratio. I think it's significantly thinner than my hand, significantly thinner than this. Turbulent velocity. Again, we know from the Doppler broadening of spectral lines in the Milky Way, we know it fairly well, 10 kilometers per second, very close to the speed of sound. By the way, it's a remarkable figure. Then people started measuring turbulent velocities in galaxies as soon as observations of the H1, 21 centimeter radial line, became possible. And then it was discovered very quickly that this turbulent velocity of the order of 10 kilometers per second behaves like a physical constant. It's everywhere. It's the same everywhere. It's the same, doesn't vary much around the radius of the galaxies, not only the Milky Way, external galaxies as well. It doesn't change much from one galaxy to another. In all spiral galaxies, of all morphological types, at all distances from the center, it's probably equal to 10 kilometers per second. Perhaps it has its explanation. This perhaps means that the source of turbulence is very strong. So the amount of energy injected into turbulent flow is high. So that the turbulence is as intense as it can be. But then, speed of sound is a natural upper limit. All the extra velocity will be quickly converted into heat. And then, this means, but the speed of sound is a function of temperature, square root of temperature, right? This means that the gas temperature is almost constant and equal to 10,000 degrees Kelvin almost everywhere. Again, it's understandable that temperature of the gas is controlled by the energy injection and the radiative cooling. And radiative cooling depends on chemistry and density. This means that the physical conditions are, in all these cases, are similar. Chemical composition is the same. The physical mechanisms of cooling are the same. So the gas, first, everywhere. There was a very important idea published in 1965 by George Field about thermal instability, who showed that the interstellar gas is thermally unstable. It splits in two stable phases. And the stable phase, guess yourself what's the temperature of the stable phase for realistic cooling curve and heating. 10,000 kelvins. So there is a thermally stable phase of interstellar gas which has temperature of 10,000 kelvins. This corresponds to the speed of sound of 10 kilometers per second. This is where the turbulent velocity is. So remarkably, you can take this 10 for virtually all galaxies. Yes, please.
It is only for spiral galaxies.
Yes.
What
yes.
happens in elliptical galaxies?
In elliptical galaxies, there the turbulent velocities must be closer to the virial velocities, of the order of what? More than half, of the order of 100 kilometers per second. Because the gas in elliptical galaxies is very hot. It has they're very similar to clusters of galaxies in this respect. It's a very hot gas of million degrees kelvins in temperature, and speed of sound there, or virial speed, is of the order of 100 kilometers per second. So you expect 100, but it's just a theory. There are no observations telling you what is the turbulent velocity in elliptical galaxies. These are just rough estimates that you can make. There are no observational data. Again, because the gas is thermal, there are no spectral lengths. The same problem is in clusters of galaxies. And turbulent scale is of the order of 1/10 of kiloparsec. So all these variables have more or less strong and convincing observational grounds. So we have very little freedom to change anything on the left-hand side. Now, let's estimate the dynamo parameters. I'm using Krause's formula. And here, of course, this is just an order of quantity estimate. But still, in this order of quantity estimate, I will be using the observed quantities. Half a kilometer per second. So, out of 10 kilometers per second, or half of it, half of a kilometer, is helical. So this is the measure, the ratio of these two numbers is the measure of how helical is the interstellar turbulence. 4% or 5%. Of the, well, in Kenji you will have the square, so it's slightly helical. Turbulent diffusivity, mixing length, you get 10 to 26 centimeters squared per second. Fine. Now we know alpha, we know beta, we know h. We can calculate our alpha for the one. Our omega. We know omega. We can differentiate with respect to r. We know h. We know beta. 10. Dynamo number. Minus 10. Minus 10. So we expect that near the sun, the dynamo number is close to sort of 10. But look at this. D omega by dr. D omega by dr is a function of r. R d omega by dr, again, will vary as 1 over r. At the 10 kiloparsecs, we shall have 10. At half the distance from the center, 5 kiloparsecs, this will be twice as much. It will be minus 20. At 1 kiloparsec, it will be 100. The dynamo number will be 100. So the dynamo number increases towards the center of the galaxy as 1 over r. Moreover, in some other galaxies, which rotates faster than 200. Again, dynamo number will be larger. And people systematically forget about it. They take these estimates and now think that it applies to all galaxies, to all positions in all galaxies. Wrong. It's wrong. Even within the Milky Way, deeper inside the Milky Way, this number will be significantly larger. So it's worth having this in mind. But these are the standard estimates which you can find in many books of ages. The only additional thing is that it's important to remember that there are just one position in just one single galaxy, where we live. And now, here we have our equations, right? And of course, the idea of solving them using complicated methods before you know what are the general properties of solution is a risky business. You want first to have something simple. And then you can do something for which, if you do this at an examination on differential equations, for the idea I will present now, you can be either kicked away from the exam and fail badly, or get the highest mark. What I'm suggesting to do is to replace all the derivatives by rationals. Replace d by dz by 1 over h. Replace d by 2 by dz squared by 1 over h squared. This way you will gain minus, right? Because this operator is negative definite. So it must be minus. a horrible idea, right? Replacing derivatives by ratios. But it works fantastically well in this case, for a simple reason. Later, I will argue that the solution is a very simple form. These equations, if you solve them honestly and applying quite a significant effort, you will show that to the lowest approximation, B is just simply depends on Z, plus cosine of Z. So this means that this approximation is much better than it looks. It's much better than it looks. Let's see what will happen. So this becomes 1 over h, this becomes minus 1 over h squared, this is minus 1 over h squared. So what I get is algebraic equation for Br and B5. I will assume now that B, for a linear problem, if alpha and beta don't depend on time, then B depends on time exponentially with growth rate gamma. And I get a system of algebraic equations. As usual, I take the determinant, equate it to 0 to have non-trivial solutions, and immediately get the dispersion relation, the dependence of growth rate on the parameters. Let's look here, beta over h squared. This is the inverse turbulent diffusion time. So the growth rate scales with the turbulent diffusion time. What I have here is first minus 1. If d is equal to 0, it's always negative. But if d is negative and large, then this term can be positive and make gamma positive. And from this you can immediately get the critical value of the dynamo number. For the dynamo number of order 1, you will get gamma positive. You can immediately calculate, having done this, you can now take any of these equations and calculate the ratio of Br to B5, which is known as a pitch angle. Immediately you get this alpha GH, right? This is equal to gamma plus BH squared is equal to G alpha over H. G alpha over H. Look at this. R alpha over R omega. What is R alpha? 1. What is R omega? 10. 1/10 square root 1/3. 1/3 of the radian is 20 degrees. Spot on. Just in the middle of the observed range. Just in the middle of the observed range. And it was, in fact, when we observed, when you have a theory, it's very unsatisfactory not to be able to compare it with observations. But this is a very simple, one-dimensional, kinematic theory. How to compare it with observations? Because I know that galaxies are not linear. I know that the galaxies are not that simple. Still, I have to isolate some features in my solution which are realistic. Otherwise, the solution is useless, right? Discussing a model which has no realistic features is pointless. So, what is realistic here? And then the idea was that even if nonlinear effects will distort my solution, the ratio of the components can be distorted perhaps less than the components themselves. So there was a hope when we developed this, that this ratio can be more robust than other parameters of the solution. And therefore, from the very beginning, we started comparing the pitch angle. So, and this is a readily observable quantity. And indeed it worked. I should say that if you make a nonlinear model, and make this nonlinearity like this algebraic alpha function, the agreement will become worse. First, I couldn't understand why. Now, perhaps I understand, just because it's a wrong type of nonlinearity. But with more realistic types of nonlinearity, we haven't done it yet. I hope that Andrew Smith could get a better estimate for modern nonlinearities of this pitch angle very soon. So, but this is a fantastic success. With this very simple model, having done most horrible, perhaps, maybe good, approximations, you immediately hit the middle of the range of an observable quantity. And now you remember that the frozen-in magnetic field in a similar, simple estimates was giving you something like -1 degree. This is a huge achievement. It was very encouraging. This was important. When we derived this estimate and compared it with observations, it was very encouraging. So, what we can conclude? First, it is clear from this formula that the dynamo is as any other dynamo, is a threshold phenomenon. This d must be larger than a certain critical value. In this simple model, this critical value is equal to 1 or -1. D must be negative. If d by modulus is less than 1, gamma will be negative. So the dynamo is a threshold signal. Second, in galaxies, dynamo number is minus 10. A more accurate solution will show you that the critical number is in fact very close to minus 10. But still, now we cannot rely on this one. One was obtained here just because we take oversimplified solution here. So now we need to calculate this d critical and compare it with the dynamo number to see if indeed we can explain magnetic field near the sun. The pitch angle of magnetic field fits very well the observations. Again, a skeptical person will say, okay, fine, it's a coincidence. Of course it's pure coincidence. You took an absolutely unrealistic, one-dimensional, linear model and now claim that it explains observations in multidimensional and non-linear galaxies. Yes, perhaps it's just coincidence, but it's worth exploring. At least up to now, everything is fine. What else? Moreover, now let's see how this pitch angle will depend on radius. Because observations indicate, this is minus here, right? 0 is here, pitch angle is equal to 0 is here, large magnitude of pitch angle is here. With radius, the magnitude of the pitch angle decreases. Can we explain this? So, R alpha divided by R omega. If I use this estimate here, I immediately get that pitch angle is of the order of the turbulence scale divided by the scale height of the disk. And in the first lecture, I argued that the scale height of the disk grows exponentially with radius. If L0 doesn't grow that fast, immediately I conclude that the magnitude of the pitch angle decreases with radius, exactly as observed. The primordial model gives an opposite, predicts an opposite behavior. In the primordial model, obviously the magnetic field is uniform outside the disk. By continuity, the pitch angle will be closer to 90 degrees as you move outwards. So this trend is opposite to what the primordial field would predict. But it was never discussed by people who develop primordial theory. They never look into all details. They always concentrate on one feature. For example, let's explain the magnitude of magnetic field. You make estimates, say primordial theory can explain the strength of magnetic field. References, submitted, published. Next paper. Let's explain the pitch angle of magnetic field. Submitted, but one paper doesn't explain the pitch angle, the other paper doesn't explain the strength. They together, they don't form the complete picture, though they're written by the same person. And this subcultures, they never even touched that. There is no way to explain this behavior with primordial theory, and it emerges naturally with dynamo models. I must end now for today. Thank you.
Thank you.
Questions, please?
And you started with wrapping up a magnetic field and no axis-symmetric magnetic field by differential notation. And you said, okay, it has the resulting field has the properties of galactic fields, but it would decay.
Yes. Not supported by the right-hand side, right?
We need a dynamo.
Yes.
And then you spoke with dynamos, and only on axis-symmetric dynamos.
Yes.
Not M equal 1.
Yes.
How I should bring these two ideas together?
But why not? This field is axially symmetric, right?
Yeah.
In this diagram, everything is axially symmetric. Large scale field. These deviations from axial symmetry are small scale. They are parameterized by alpha and beta. But the dominant field from observations is also axisymmetric. And I deliberately put here, it's not the homogeneous non-axisymmetric field which passes through the disk. I deliberately started with an axisymmetric field here. It is axisymmetric, right? I started with axisymmetric field. I showed that it will produce here there are no reversals. The direction of the arrow here is like this, and here too. So axisymmetric field distorted by differential rotation still produce axisymmetric field. And this axisymmetric field, due to the action of alpha effect, will again produce axisymmetric field.
Yeah, I see. So differential rotation makes a strong toroidal field in
Yes.
axisymmetric.
Axisymmetric. It's not m equal to 1 mode. Here, this is m equal to 0 mode.
First, a non-axisymmetric field.
Hmm?
What you consider first a non-axisymmetric field.
No, yes, yes. Here, these are already, here I discuss how the dynamo already works, how the eigenfunction is constructed. But what I should do then, if I want to discuss how the dynamo starts, right? Then I will consider the seed field, right? Then I will say perhaps the seed field will have m equal to 1 mode. So its projection onto this mode was equal to 0.
Okay.
But then still I will get away with that. I will say the system is turbulent. It will tangle this field, m equal to 1. It will produce small-scale field, which will have non-zero projection on this eigenmode. And the machine will start working. Or fluctuation dynamo will produce turbulent magnetic field, which will have non-zero projection onto this mode. And again, it will start the dynamo. So I don't think there is a problem with the seed field. Whatever is any magnetic field in the galaxy would be good enough to launch this growth. Right?
Yeah.
Thank you.
Yes, please. What?
So because of Calling theorem, all of the non-axis symmetry now is hidden in the alpha generator.
Absolutely, yes.
Alright? And based on what is being known on structure of galaxy is what is the non-axis symmetry? Is the wrapping of the spiral, or what is the non-axis symmetry?
Well, this winding up a differential rotation can be axisymmetric.
No, this I understand. It's all
Yes.
hidden in alpha.
The deviations from axial symmetry mostly come, first of all, from the spiral arms. These are the strongest deviations from axial symmetry in an average galaxy, in a typical galaxy. But this I will be able to include later. Because what I can do, I can first develop an axisymmetric model, and then this is what Kondo did with Leon Mestel. After that we say, now I will modulate, say, alpha or alpha most often, by a spiral pattern, and I will calculate the perturbation due to that. It works.
Well, that's all right. So you're saying that the alpha is generated from non-axisymmetric motions, and this non-axisymmetric motion is due to the structure of the galaxy.
No, from turbulence.
So
This is where from alpha comes, from these motions. And these are random turbulent motions.
Yeah, they have to be random of a certain kind because they have to lack reflectional symmetry. If the
This is why.
So you're assuming this from the beginning.
What do you mean assuming? I'm not assuming that it rotates. I know that the galaxy rotates, and I know that it's density stratified.
Okay, so it's
This I'm not assuming.
all right, fine. It's a combination of rotation plus stratification. Let's say that the turbulence will not be mirror symmetric.
Yes, yes.
Okay.
And of course, it would be. I understand your concern. I share your concern. Can we see this helicity?
I think we can, but I just
You know,
want to make sure that
We discussed many times with observers if you can observe this helicity. It seems to be a difficult thing to do, mainly because the amount of helical twisting is just a few percent of the total velocity. So it's probably hard, but not impossible. Maybe in some future we shall be able to measure this twisting, just observation, on average, of course, statistically. So if, for example, you observe a certain parameter in the northern galactic hemisphere, well, velocities. Then southern hemisphere, you compare the two to calculate the difference.
I'll come back to it in what I'll say, but it's experimentally known now that if you have turbulence, there's very little, even if it's helical turbulence, there's very little helicity that will survive down the scales. But if you have rotation and stratification, you have tremendous amount of
Experimentally,
experimentally.
will you give me, let's discuss, will you give me references, right? It's important. Here. Thank you.
So when do you put I 1 over h and when do you put ik?
The same thing.
No, it's not. One
Why not?
gives you oscillatory solutions, the other one doesn't.
1 over h I put in finite space and I k in infinite space, right? This is the difference here. But on the other hand, I can also put IK. I can develop here WKB solutions, which will also have IK, but K will be a function of position, right? For WKB. And there are such asymptotic solutions of these equations also in WKB for large dynamo numbers. So that I will be discussing in the next lecture the solutions for small dynamo number, when these two terms can be considered as perturbation. There are also asymptotic solutions for large dynamo number, both boundary layer type and WKB.
Okay. All right. If there are no further questions, then let's thank you again.